Welcome to Tesla AI Day 2022. As you know, last year it was just a person in a robot suit. We're going to talk about the advancements in AI for full self-driving, as well as how they apply to, more generally, to real-world AI problems like a humanoid robot, and even going beyond that. What we're doing here at Tesla could make a meaningful contribution to AGI.
I think the bot got some moves too. So this is essentially the same full self-driving computer that runs in your Tesla cars, by the way.
This is literally the first time the robot has operated without a tether. Was on stage tonight. The robot can actually do a lot more than we just showed you. We just didn't want it to fall on its face. Yeah.
Yeah, we wanted to show a little bit more what we've done over the past few months with the bot, and just walking around and dancing on stage. Just humble beginnings, but you can see the autopilot neural networks running as is, just retrained for the bot directly on that new platform. That's my watering can.
Yeah, when you see a rendered view, that's the robot. That's the world the robot sees. So it's very clearly identifying objects. Like this is the object it should picking it up. Yeah.
We use the same process as we did for Autopilot to collect data and train neural networks that we then deploy on the robot. That's an example that illustrates the upper body a little bit more. Something that we'll try to nail down in a few months, over the next few months, I would say, to perfection.
This is really an actual station in the Fremont factory as well that it's working at.
What you saw was what we call Bumble C. That's our sort of rough development robot using semi-off-the-shelf actuators. But we actually have gone a step further than that already. The team's done an incredible job. And we actually have an Optimus bot with fully Tesla-designed and built actuators, battery pack, control system, everything. It wasn't quite ready to walk, but I think it will walk in a few weeks. But we wanted to show you the robot, something that's actually fairly close to what will go into production, and show you all the things it can do. So let's bring it out.
Do it.
So here you're seeing Optimus with with the degrees of freedom that we expect to have in Optimus Production Unit 1, which is the ability to move all the fingers independently, to have the thumb have 2 degrees of freedom, so it has opposable thumbs, and both left and right hand, so it's able to operate tools and do useful things. Our goal is to make a useful humanoid robot as quickly as possible. And we've also designed it using the same discipline that we use in designing the car, which is to design it for manufacturing such that it's possible to make the robot in high volume at low cost with high reliability. So that's incredibly important. I mean, you've all seen very impressive humanoid robot demonstrations, and that's great, but what are they missing? They're missing a brain. They don't have the intelligence to navigate the world by themselves. And they're also very expensive and made in low volume. Whereas Optimus is designed to be an extremely capable robot, but made in very high volume, probably ultimately millions of units, and it is expected to cost much less than a car.
We'll just bring it directly to the right here.
I would say probably less than $20,000.
What other company would have the balls and confidence to design a product like this with mass production in mind?
Now, there's still a lot of work to be done to refine Optimus and improve it. Obviously, this is just Optimus version 1. And that's really why we're holding this event, which is to convince some of the most talented people in the world, like you guys, to join Tesla and help make it a reality. The potential, like I said, is really boggles the mind, because you have to say, like, what is an economy? An economy is sort of productive entities times their productivity, capita times output, productivity per capita. At the point at which there is not a limitation on capita, it's not clear what an economy even means at that point. An economy becomes quasi-infinite.
The potential for this product is bigger than any other product that's ever existed in the history of humankind. I mean, this is nuts.
This means a future of abundance, a future where there is no poverty, where you can have whatever you want in terms of products and services. It really is a fundamental transformation of civilization as we know it. Tesla as an entity doing this, being a single class of stock publicly traded, owned by the public, is very important and should not be overlooked. I think this is essential, because then if the public doesn't like what Tesla's doing, the public can buy shares in Tesla and vote differently.
There's something to be said in that it would be pretty scary if there was a private company that was designing this.
It's very important that the corporate entity that makes this happen is something that the public can properly influence. Self-driving cars will certainly have a tremendous impact on the world. I think they will improve the productivity of transport by at least a half order of magnitude, perhaps an order of magnitude, perhaps more.
An order of magnitude is like 10 times. So basically he's saying that self-driving vehicles will improve the productivity of transport by at least 5 to 10 times.
Optimus, I think, has maybe a 2 order of magnitude potential improvement in economic output.
2 orders of magnitude is 100 times. So he's saying that, Optimus has the potential to improve our economic output by 100 times. This might all sound pretty crazy, but if you just look at the fundamentals and what's possible, like, this is all within the realm of possibility. And not only is it within the realm of possibility, just looking at the rate of improvement of this type of technology, everything points in this direction. You could argue that this sounds kind of crazy, but this is inevitable. It's more just a question of when and how fast this all comes to fruition.
It's not clear what the limit actually even is. But we need to do this in the right way. We need to do it carefully and safely, and ensure that the outcome is one that is beneficial to civilization and one that humanity wants.
So last year we unveiled the Tesla Bot concept, but a concept doesn't get us very far. We knew we needed a real development and integration platform to get real-life learnings as quickly as possible. So that robot that came out and did the little routine for you guys, we had that within 6 months, built, working on software integration, hardware upgrades over the months since then. But in parallel, we've also been designing the next generation, this one over here.
Talk about pace of innovation, man.
Put your fingertip on the chair in front of you. You'll notice that there's a huge range of motion that you have in your shoulder and your elbow, for example. Without moving your fingertip, you can move those joints all over the place. But the robot, its main function is to do real useful work. And it maybe doesn't necessarily need all of those degrees of freedom right away. So we've stripped it down to a minimum sort of 28 fundamental degrees of freedom, and then, of course, our hands in addition to that. So let's talk about this latest generation in some detail, shall we? So on the screen here, you'll see in orange our actuators, which we'll get to in a little bit, and in blue our electrical system. And we have our first development platform. We have both research and execution to draw from for this design. Along the way, we're going to optimize for things like cost and efficiency, because those are critical metrics to take this product to scale eventually. So in the middle of our torso, actually it is the torso, we have our battery pack. This is sized at 2.3 kilowatt hours, which is perfect for about a full day's worth of work. We're also leveraging both our vehicle products and our energy products to roll all of those key features into this battery. So that's streamlined manufacturing, really efficient and simple cooling methods, battery management, and also safety. And of course, we can leverage Tesla's existing infrastructure and supply chain to make it. Also in our torso, we have our central computer. So as you know, Tesla already ships full self-driving computers in every vehicle we produce.
So basically, Tesla's already producing the computer for this robot at scale. This is what economies of scale look like.
We want to leverage both the autopilot hardware and the software for the humanoid platform. It's going to do everything that a human brain does. Processing vision data, making split-second decisions based on multiple sensory inputs, and also communications. So to support communications, it's equipped with wireless connectivity as well as audio support. And then it also has hardware-level security features, which are important to protect both the robot and the people around the robot.
Tesla have the capabilities to analyze highly complex systems. They don't get much more complex than a crash. You can see here a simulated crash from Model 3 superimposed on top of the actual physical crash. It's actually incredible how accurate it is. Just to give you an idea of the complexity of this model, it includes every nut, bolt, and washer, every spot weld, and it has 35 million degrees of freedom. It's quite amazing. And it's true to say that if we didn't have models like this, we wouldn't be able to make the safest cars in the world. So can we utilize our capabilities and our methods from the automotive side to influence a robot? Well, we can make a model, and since we had crash software, we're using the same software here, we can make it fall down. And the purpose of this is to make sure that if it falls down, ideally it doesn't, but it's superficial damage. We don't want it to, for example, break its gearbox and its arms. That's equivalent of a dislocated shoulder of a robot. Difficult and expensive to fix. So we want it to dust itself off, get on with the job it's been given. This is showing just simple walking. We can create the stresses in all the components. That helps us to optimize the components. We want to make thousands, maybe millions. We haven't got the luxury of making them from carbon fiber and titanium. We want to make them from plastic. Things are not quite so stiff. If you think about it, sorry about this, but we're just bags of soggy jelly and bones thrown in. We're not high frequency. If I stand on my leg, I don't vibrate at 10 hertz. People operate at low frequency, so we know the robot actually can. It just makes controls harder. So we take the information from this, the modal data and the stiffness, and feed that into the control system. That allows it to walk. Just changing tack slightly, looking at the knee. We can take some inspiration from biology, and we can look to see what the mechanical advantage of the knee is. It turns out it actually represents quite similar to 4-bar link, and that's quite non-linear. That's not surprising, really, because if you think when you bend your leg down, the torque on your knee is much more when it's bent than it is when it's straight. So you'd expect a non-linear function. And in fact, the biology is non-linear. This matches it quite accurately. So that's a representation. The 4-bar link is obviously not physically a 4-bar link. As I said, the characteristics are similar. But me bending down, that's not very scientific. Let's be a bit more scientific. We've played all the tasks through this graph, and this is showing picking things up, walking, squatting, the tasks I said we did on the stress. And that's the torque seen at the knee against the knee bend on the horizontal axis. This is showing the requirement for the need to do all these tasks. I've then put a curve through it, surfing over the top of the peaks, and that's saying this is what's required to make the robot do these tasks.
So I would like to talk to you about the design process and the actuator portfolio. The most important thing that matters here is energy, mass, and cost. We are carrying over most of our designing experience from the car to the robot. So in the particular case, you see a car with 2 drive units. And the drive units are used in order to accelerate the car 0 to 60 miles per hour time or drive a city drive cycle. While the robot that has 28 actuators, it's not obvious what are the tasks at actuator level. So we have tasks that are higher level, like walking or climbing stairs or carrying a heavy object, which need to be translated into joint specs. Therefore, we use our model that generates the torque speed trajectories for our joints, which subsequently is going to be fed in our optimization model to run through the optimization process. This is one of the scenarios that the robot is capable of doing, which is turning and walking. So when we have this torque speed trajectory, we lay it over an efficiency map of an actuator, and we are able, along the trajectory, to generate the power consumption and the energy, cumulative energy for the task versus time. So this allows us to define the system cost for the particular actuator and put a simple point into the cloud. Then we do this for hundreds of thousands of actuators by solving in our cluster. And the red line denotes the Pareto front, which is the preferred area where we will look for optimal. So the X denotes the preferred actuator design we have picked for this particular joint. So now we need to do this for every joint. We have 28 joints to optimize, and we parse our cloud. We parse our cloud, again, for every joint spec, and the red axis this time denote the bespoke actuator designs for every joint. The problem here is that we have too many unique actuator designs, and even if we take advantage of the symmetry, still there are too many. In order to make something mass manufacturable, we need to be able to reduce the amount of unique actuator designs. Therefore, we run something called commonality study, which we parse our cloud again, looking this time for actuators that simultaneously meet the joint performance requirements for more than one joint at the same time. So the resulting portfolio is 6 actuators, and they show in a color map at the middle figure. And the actuators can be also viewed in this slide. We have 3 rotary and 3 linear actuators, all of which have a great output force or torque per mass. In order to demonstrate the force capability of our linear actuators, we have set up an experiment in order to test it under its limits. So our actuator is able to lift a half-ton, 9-foot concert grand piano. This is a requirement. It's not something nice to have. When they are directly driven, our quadricep muscles can do the same thing. It's just that the knee is an up-gearing linkage system that converts the force into velocity at the end effector of our heels for purposes of giving to the human body agility.
For our robotic hand design, we were inspired by biology. We have 5 fingers and an opposable thumb. Our fingers are driven by metallic tendons that are both flexible and strong. We have the ability to complete wide aperture power grasps while also being optimized for precision gripping of small, thin, and delicate objects. So why a human-like robotic hand? Well, the main reason is that our factories and the world around us is designed to be ergonomic. So what that means is that it ensures that objects in our factory are graspable, but it also ensures that new objects that we may have never seen before can be grasped by the human hand and by our robotic hand. Some basic stats about our hand is that it has 6 actuators and 11 degrees of freedom. It has an in-hand controller, which drives the fingers and receives sensor feedback. Sensor feedback is really important to learn a little bit more about the objects that we're grasping, and also for proprioception. And that's the ability for us to recognize where our hand is in space. One of the important aspects of our hand is that it's adaptive. This adaptability is involved essentially as complex mechanisms that allow the hand to adapt to the objects that's being grasped. Another important part is that we have a non-back drivable finger drive. This clutching mechanism allows us to hold and transport objects without having to turn on the hand motors.
Spring-loaded, mainly what spring-loaded allows us to do is allows us to have active opening. So instead of having to have two actuators to drive the fingers closed and then open, we have the ability to have the tendon drive them closed and then the springs passively extend. And this is something that's seen in our hands as well, right? We have the ability to actively flex, and then we also have the ability to extend.
So for example, our computer vision neural networks were ported directly from autopilot to the bot's situation. It's exactly the same occupancy network that we'll talk into a little bit more details later with the autopilot team that is now running on the bot here in this video. The only thing that changed really is the training data that we had to recollect. We're also trying to find ways to improve those occupancy networks using work made on neural radiance fields to get really great volumetric rendering of the bot's environments. For example, here, some machinery that the bot might have to interact with.
So far, we've seen how incredible Tesla's engineers are and how they tackle the problem of building the body of the robot. But I think where Tesla really shines and where they're 5 to 10 years ahead of everyone else is the brain of the robot, the Tesla vision. The brain of the Tesla bot is already so advanced. I mean, understanding the world around it through vision, identifying objects as well as predicting their velocities, future behaviors, future movements, moving through the real world and understanding where everything is relative to the Tesla bot. Planning and split-second decision-making, collecting more real-world data, relaying it back to a supercomputer that continues to improve models and retrain the robot, essentially setting this robot up to continue learning at an exponential rate.
Another interesting problem to think about is, in indoor environments, mostly with absence of GPS signal, how do you get the bot to navigate to its destination? Say, for instance, to find its nearest charging station. So we've been training more neural networks to identify high-frequency features, key points within the bot's camera streams, and track them across frames over time as the bot navigates through its environment. And we're using those points to get a better estimate of the bot's pose and trajectory within its environment as it's walking.
And oh my God, as you can see from this, the robot's essentially in real time 3D mapping its surroundings and doing what we humans do. And basically, when we enter a building and walk through a few hallways, we pick out certain points, identify them, and we basically create a 3D map of our understanding of the world of the building that we're in. And we use that to navigate because the Tesla bot isn't always going to have access to GPS or the internet. I mean, this is so exciting. Like, all of the features of the Tesla's computer are very close to what we do as humans when we navigate the real world.
We also did quite some work on the simulation side. And this is literally the autopilot simulator, to which we've integrated the robot's locomotion code. And this is a video of the motion control code running in the autopilot simulator, showing the evolution of the robot's walk over time. And so as you can see, we started quite slowly in April and started accelerating as we unlock more joints and deploy more advanced techniques like arms balancing over the past few months. And so locomotion is specifically one component that's very different as we're moving from the car to the bot's environment.
Reality is way more complex than any sim or model. Also, the robot is not simplified. It's got vibrations and modes, compliance, sensor noise, and on and on and on. So what can we do about it? Well, we measure reality. We use sensors and our understanding of the world to do state estimation. And here you can see the attitude and pelvis pose, which is essentially the vestibular system in a human, along with the center of mass trajectory being tracked when the robot's walking in the office environment. Now we have all the pieces we need in order to close the loop. So we use our better bot model, we use the understanding of reality that we've gained through state estimation, and we compare what we want versus what we expect that reality is doing to us in order to add corrections to the behavior of the robot. Here, the robot certainly doesn't appreciate being poked, but it does an admirable job of staying upright. The final point here is a robot that walks is not enough. We need it to use its hands and arms to be useful. Let's talk about manipulation.
We wanted to manipulate objects while looking as natural as possible, and also get there quickly. So what we've done is we've broken this process down into 2 steps. First is generating a library of natural motion references, or we could call them demonstrations. And then we've adapted these motion references online to the current real-world situation. So let's say we have a human demonstration of picking up an object. We can get a motion capture of that demonstration, which is visualized right here as a bunch of keyframes representing the locations of the hands, the elbows, the torso. We can map that to the robot using inverse kinematics. And if we collect a lot of these, now we have a library that we can work with. But a single demonstration is not generalizable to the variation in the real world. For instance, this would only work for a box in a very particular location. So what we've also done is run these reference trajectories through a trajectory optimization program, which solves for where the hand should be, how the robot should balance during when it needs to adapt the motion to the real world. So for instance, if the box is in this location, then our optimizer will create this trajectory instead.
I think the first thing within the next few weeks is to get Optimus at least at par with Bumble C, the other bot prototype you saw earlier, and probably beyond. We're also going to start focusing on the real use case at one of our factories, and really going to try to nail this down and iron out all the elements needed to deploy this product in the real world. I think it's pretty amazing. All of this was done in barely 6 or 8 months. Thank you very much.
Amazing is an understatement. I mean, within 6 to 8 months, they were able to build a robot from scratch, start collecting data using that prototype, Bumble C, in order to help design a second robot, which it seems like they've already fully designed the new Optimus with all their own actuators and hardware and software. And now they believe within a few weeks they should be able to get this new prototype up to par with their first prototype. All of this within 6 to 8 months. I just can't imagine, you know, in a year from now, AI Day 2023, like what do you guys think that's gonna look like? I mean, it's only gonna get better from here. This is like the very beginning. You know, Tesla just started this project 8 months ago. This is like the beginning, and they already have this much to show. So like, I don't know, like what do you guys think that Optimus is going to be doing a year from now, 2 years from now, 3 years from now? I don't know about you guys, but I'm really, really excited to see.
Produce the robot as quickly as possible and have it, like I said, be useful as quickly as possible. We're trying to follow the goal of fastest path to a useful robot that can be made at volume. And I'm sure people will think of all sorts of creative uses for this robot.
Yeah, I think we'll have ways to remote operate the robot and intervene when it does something bad, especially when we are training the robot and bringing it up. And hopefully we design it in a way that we can stop the robot from, if it's going to hit something, we can just like hold it and then it'll stop. It won't like crush your hand or something. And those are all intervention data.
Obviously able to do simple instructions or even intuit what it is that you want. So you could give it a high-level instruction, and then it can break that down into a series of actions and take those actions. The number of situations where Optimus is useful will grow exponentially. Within 3 to 5 years, you could probably receive an Optimus.
Money thoughts.